Hello, today we are going to talk more about this balancing chemical equations, go over some of the basics from last week, and introduce some new information. Okay, so some of the common symbols that I did touch on last week that I just want to make sure we all are on the same page on. You're going to see this symbol when we are adding two of the reactants together. Okay, so you can either have a reactant plus a reactant, and that would be two separate chemicals being added into the same thing to produce, most times, two different products. Now, we're going to talk later about how sometimes it won't be two, but when you see this, you know that they're being added together, okay, which is a lot like what it means in math, so not too difficult, all right? This also, in a word equation, which we're going to talk about in a second, if it's talking about the reactants, it will say, you know, if this was maybe calcium on this side and water, it would say calcium reacts with water to produce. So the line would actually be afterwards. So this symbol can also, in a word equation, mean reacts with. Okay. All right, this is the what is going to be produced. Okay, so a lot of times you'll see the word produced on the reactants. It also shows the direction. So the reactants always go in front of the arrow, and then behind the arrow where the arrow is pointing is always where the products are. And oops. And this always just shows us what is going to be produced. Okay, and then I have another arrow down here, and this arrow is the same thing, but we can write what is going to make it produce. So sometimes you can put in two chemicals, and they'll just automatically reaction will start. Other times you need to maybe stir it to make the reaction happen, or maybe you need to add heat, or for some reason you need some kind of other catalyst. And so they would actually write it above the arrow. And I believe I did this on Friday on the board, so this shouldn't be completely new to you. So an arrow with something above it is something that is going to make the reaction happen. Okay. Now these are our states of matter. Okay, so I'm just going to write states of matter. Okay, and so when this is behind a chemical compound, this means that it is a solid. So you might see something like NaCl, and then it would say this, and so this would mean it's in its crystalline form. Okay, water is our only liquid. Okay, so the only time you would ever use an L is when it is behind H2O. Okay. G obviously means gas, and this is usually a product. Okay, you're usually going to see gases in the product, so you're going to see like H2 gas, and that's going to be something that's produced. Okay, and then this one means aqueous, and aqueous just means something dissolved in water. A solute, which remember is like some kind of solid dissolved in water. Okay, and so a lot of times, you know, like so if we use the same example, NaCl, and if you see an AQ behind it, now you know that it's salt dissolved in water. So this is salt water, okay, compared to the salt as a crystal. And you always remember that our acids are always aqueous. Acids are always aqueous. All right. All right, now here's just some basic terminology. The word equation that was introduced to you on Friday in your quiz. It was the last question when we had the calcium plus water makes calcium hydroxide and hydrogen gas. Okay, and it's written literally as a sentence. And so you're going to see things like reacts with to produce a solid, iron, and a hydrogen gas. Okay, so this really tests if you know how to write these ionic and covalent compounds, your acids And so you really need to review the previous chapters if you feel like you're having problems naming ionic and covalent compounds and acids, because they're still here. We're still going to be using them. Alright, and so then the skeletal equation, this can be written from a word equation, and what this really is, it's just an unbalanced equation. So if from the word equation, we said solid calcium reacts with water to produce, and it just basically has the states of matter and all of the equations correct. So calcium hydroxide, of course that's aqueous, plus H2 gas. Okay, so this would be considered a skeletal equation because nothing is balanced. Okay, because if we're going to balance this, we'd put a 2 in front. So an unbalanced equation where it has the states of matter. So we need the states of matter, and we'd also need all of the formulas written correctly. Okay, so you'd make sure you need that 2 there, and you need to know what hydroxide is. Okay. Alright, so the entire point of this chapter is the law of conservation of mass, and that's basically that each side of the equation is equal to each other. Okay, so the reactants, and we're talking about the number or the mass of the reactants is equal to the number or mass of the products, because you can't create mass and you can't destroy mass. This is just like the law of conservation of energy that you learned about in physical science. We can't just create and get more hydrogens on one side than we did the other. Okay, so you would have to, we can't just, now we have 4 hydrogens over here that just didn't come from anywhere. So now that's why we have to balance it to say we use 2 water molecules to react with every 1 calcium atom to produce calcium hydroxide and to make it work. So we need 2 of these to react with 1 of these to produce this. Okay, so it's really just making sense and like visualizing those molecules and saying every 2 molecules of water is going to react with 1 atom of calcium. Alright, and then of course the balanced chemical equation, we're using those coefficients. Okay, so this just has the coefficients, and this is how we are balancing it. Okay, so if I was going to balance this one, we put the 2 up there. And then the subscripts, those of course are these little guys down here that we have been talking about the last 2 chapters. These cannot be changed when balancing. Okay, you cannot just say, oh, I need 2 of those and change it to O2, because that no longer is an okay ionic bond. That won't work. Okay, so never ever ever change these. It has to stay a 3. Okay, and then the coefficients, of course, is the only thing you can change. Okay, so we know that if we need Al2O3 and we need 6 oxygens on the other side, okay, so we have a 3O2 and we need 6 oxygens, we're going to have to put a 2 in front of this. Okay, and there's nothing else we can do, and now we have 6 and 6, and so we're balanced. Alright, now we're going to check to make sure everybody's counting atoms correctly. Sometimes when we get the subscripts and parentheses and all these different things, I'm going to go ahead and do these 3 for you, and then you can go ahead and pause the video and do these last 4. And this is something Mr. Fitzsimmons and I can check on Monday. Okay, so this 3 obviously goes out to the calcium, so we have 3 calciums, and it also goes out to the fluorine. But the fluorine has 2, so you really have to think about it as their fluorine bonds. Okay, so we have these lone pairs, and we have these fluorine bonds, and there are 3 pairs of those, or 3 pairs of those, so that would make 6 total fluorines. Okay, so it's just like you're multiplying. Okay, and then in the parentheses, you know that this 4 goes to all 3 of these, but the 2 only goes to what's in the parentheses. So we have 4 beryllium, and then we have 4 times 2 oxygen, so there's 8 oxygen, and then 4 times 2 hydrogen, so there's 8 hydrogen. Alright, and then these get a little bit more complex. This one's a little more complex here. We know the 5 goes to each, okay? We know this 2 only goes to the aluminum, the 4 only goes to the oxygen, and the 3 goes to both. Okay, so we have 5 times 2 aluminum, which is 10 aluminum. And then we have 5 times 3 sulfur, which is 15 sulfur. And then we have 3 times 4, which is 12 oxygen, times 5, which gives us 60 oxygen. So you can see how those really can get big. Okay, so go ahead and pause and do those last 4 for us to make sure that you have this concept. Alright, now we're going to talk about the types of reactions. We're also going to do this as a bell ringer on Monday, so I'm just going to kind of go through it a little quickly to introduce it to you. Okay, so synthesis also means combination, and that's because 2 elements literally combine to make 1. So we have something like A plus B equals AB. So we have 2 elements, element A, element B, makes compound AB. Or these can also be compounds. So we could have something like H2, which is a compound, plus O2 makes H2O. So this would be a combination reaction. Okay? And really, it's when you have one product. Okay? Oops. All right. Decomposition is just the opposite. Okay? You start out with 1 and, oops, I don't know what I was doing there. We start out with 1 and we end up with 2. Okay? So you start out with 1 compound and it breaks apart and becomes 2. So maybe you have, I think a common one is this HGO. So mercury oxide breaks down into mercury plus oxygen. Okay, so decomposition. Single replacement, I always give people a bad time if your favorite, actor or actress came into town and you were hanging out with your boyfriend or your girlfriend, and they came into town. So this is the famous person that you've always been in love with. You might leave your boyfriend or girlfriend for them. And that's a single replacement. So A goes with C and leaves their boyfriend by themselves. Okay? So an example of a single replacement would maybe be like zinc plus copper nitrate. Okay, something like this. And so zinc is more reactive than copper, and so it actually kicks copper out. And so it becomes zinc nitrate plus copper by itself. Now, sometimes this will not occur. If this element by itself is less reactive than this element, then there will be no reaction. Okay, and so then there would be no reaction. Okay, so on this slide right here, this is called the activity series. And so this is where we actually see which things are more reactive than others. And we have basically our cations on this side, we have our anions on this side. So fluorine is the most reactive anion. So if you had something like fluorine by himself as a gas, plus sodium bromide, okay, and you put these together, the fluorine would kick bromine out, and so it becomes sodium fluoride plus bromine by himself. Okay. However, if you had potassium chloride and you added in iodine, nothing would happen. There would be no reaction. Okay, because chlorine is more reactive than iodine. Okay, so we have to use this chart. Of course, it works the same way with the cations. Okay, so we have to know which things are more reactive, and these will these are the kind of the descriptions. You won't need to know these. I'm really most concerned with you knowing if lithium is more reactive than sodium. So I've had a lot of students in the past make up little songs, and if you look at where these are on the periodic table, it'll give you a very good idea of where these are as well. Okay, and I think probably the most important would be probably these top two. Okay, because this is out of our new book, and this kind of goes a little further, so it's a good resource to look back on. But the quiz will only be over these two and this one, and this will be Monday at the end of class. Okay, so why don't you go ahead and start looking at those, and we're going to do some activities in class as well to know these, but these are for single replacement reactions. Okay, alright, so let's go back here. Now we have double replacement, and we saw lots of these in our lab, and this is when couple A and B go out on the date with couple C and D, and there's always, of course, the positive and the negative anion, the positive and negative anion. So this is the boy and the girl, the boy and the girl. And they go on the date, and everybody's talking, and they decide that, you know, maybe they're with the wrong people. So this guy ends up you know, going on a date with that girl next, and this guy goes on a date with that girl next. So A and D become new compounds, and C and B become new compounds, okay, or couples, however you want to look at it. All right, and oddly enough, in high school, me and my best friend did end up dating each other's boyfriends eventually. So this is something that is not that weird to me, but it is kind of weird. Okay, so an example of this could be, let's see, what was one from the lab maybe that we did, or let's just do any one. Okay, so let's do calcium hydroxide, since we've been talking about this, plus HCl, and this would make water plus calcium chloride. Okay. All right, of course I'm not balancing any of these. That's what we do after we figure out the type. And then a really big deal of double replacement is this neutralization, and that's where you can take an acid and a base to make water and a salt, okay, which this side is completely neutral. We can pour it down the drain. So all of our labs, when we've been doing neutralization, we've actually been doing a double replacement reaction, okay. So sodium hydroxide, we used this in lab yesterday, super strong base, and then HCl, super strong acid, react together, double replacement, these two go together, then these two go together, so we get sodium chloride plus water. So there we go. Alright, and then combustion, this one is pretty easy to identify. It's always a carbon compound, and by the way, a covalent carbon compound. Remember, carbon doesn't bond too much ionically. Carbon compound and oxygen. So like when we start up our Bunsen burners, these are always the combustion reaction. Carbon compound plus oxygen always produces water and carbon dioxide. Okay, so example of this, let's just use our Bunsen burner example. Okay, it's methane gas, which is CH4, okay, plus oxygen in the air, make CO2 plus water. Okay, so if we're talking about predicting products here, you can look here and you can say, if you couldn't see this, you could look at these two and you could try to figure out what combination would make one. Here you'd see how they break apart. Here you'd see that you'd have to check your reactivity series to see if they were going to switch places. Here they're going to switch places. You just switch their partners. And here, if you see a carbon compound and oxygen, you know it's CO2 and water. Okay, and so this is how we're going to start predicting our products. Now, the last part of this is knowing, like in our double replacement reactions specifically, which things are going to be solids, which things are going to be gases, which things are going to be aqueous, and so predicting those states of matter. And we have another chart that you need to know for that, and that's the solubility chart, which we will be having a little quiz on Wednesday. Okay, so Wednesday's quiz is going to consist of us knowing which compounds are the most soluble. So sodium, potassium, and ammonium compounds are soluble in water. So if anything bonds with sodium, anything bonds with potassium, anything bonds with ammonium, it's going to be aqueous. We know that for sure. Okay? Nitrates, acetates, and chlorates, so these are talking about the anions now, they are soluble. So they're always going to be aqueous. Okay? Chlorides are soluble, and then except if they're bonded with, so if it's silver chloride, mercury chloride, or lead chloride, they're not going to be soluble. So anything else bonded with chlorine is going to be soluble unless they're bonded with these three. And then lead chloride could be soluble if it's in hot water. Okay. And then most sulfates are soluble except if they're bonded with barium, strontium, lead, or calcium. Okay, or mercury. Okay. So if you see something like barium sulfate, you're going to know that it's going to be a solid in the product. However, if you see potassium sulfate, you're going to know it is going to be aqueous. Okay. So your quiz on Wednesday, you don't have to memorize this chart. It's going to be how you use this chart. So you're going to have to understand this chart. Okay, you're going to have this chart on your test. And then most carbonates, phosphates, and silicates are insoluble. So that means they're always going to be solids, except those of sodium, potassium, and ammonium. So back up to this one, because it says all things bonded with sodium, potassium, and ammonium are aqueous, even when they're bonded with carbonates, phosphates, or sulfonates. So when you have sodium carbonate, that is going to be aqueous. However, if carbonate is with anything else, it's going to become a solid. Okay. And in our lab, if you were to look back, when we added in our sodium carbonate solution, it was with sodium, so that's why it was in that liquid. But as soon as it went into our thing with copper, boom, it was a solid. It was that foggy paste looking stuff, and the copper carbonate was the part that was doing that. And then most sulfides are insoluble, so anything bonded with sulfur. So you have this is going to be a solid. Except, whoops, that's going to be aqueous. I didn't read because it was sodium, it'll be aqueous. But if it's, let's see, one that's not on there, lithium sulfate is going to be a solid. So you have just these couple that you would have to recognize and know that it would be aqueous with them right here. Okay? All right, I hope this clears up any questions, and I will be going over this, and Mr. Fitzsimmons will be going over this again on Monday, and we will be having that quiz over this chart here. Basically, this knowing which ones are the most reactive, okay? And then, of course, on this side as well. All right, because that's super important to be able to recognize what's going to be reacting with what. All right, hope you have a great rest of the weekend, and I will talk to you tomorrow.